So as it turns out, the new year has come out, and I've changed affiliations overnight as I was flying. So I was with Johns Hopkins. I've been with Hopkins for the last 20 years, and I've recently moved to the University of Pennsylvania. So you will see the slides are half and half between my trying to adjust to Penn, but most of the work and almost everything has been done at Johns Hopkins. So deep learning has been around now for 10, 15 years, and it's changed the way we do things. And originally, it was impactful in academic settings, like ImageNet or playing games. But today, it's really in our real life. We all use voice assistants. We all are heading into the idea that we're going to have self-driving cars. And as AI begins to impact our daily life, it's important to make sure that the predictions that AI systems make are not only accurate, but also maybe fair, robust. Even, we would like to make sure that the predictions that are made are explainable to the end users. So in this talk, I'll focus on two of these properties, namely robustness and explainability. And by robustness, what we mean is that these AI systems, even though they work very accurately, we don't know why they work when they do, and we don't know why they fail when they fail. And it turns out that it's very easy to make them fail. If you look at this image versus that image, they look nearly identical. But the prediction of the AI system, in this case, is a stop sign. In this case, is a yield sign. And if you put that into a self-driving car, you're going to be into trouble. And so how can we prevent that from happening? The second example might be you're making a clinical decision with an AI system, and you're trying to explain why you made that decision. And in this case, you predict that based on an MRI scan that you've got Alzheimer's disease with 98 probability. But why is this the case? You might want to have an explanation as to it's because, the ventricles are enlarged in a certain region. So how do we do that? So the approach that we've taken to look into both of these problems is connected to the idea of parsimonious representation, sparse, low rank. And by and large, the approach is fairly generic, you would say. We are going to take high-dimensional data, X. We're going to map it to some latent representation, Z. Actually, not necessarily latent. And then the idea is that from some representation, we're going to predict whatever we want to predict. So the key question is going to be really, what parsimonious representations are adequate in order to ensure robustness or in order to ensure explainability? In the case of robustness, and this is going to connect very well with some of the things that were talked about yesterday in the tutorial, we're going to be using block sparsity as the way to ensure that the latent representation has a particular structure that allows you to be robust to those adversarial attacks. In the case of explainability, the notion of parsimony is going to be information theoretic. We are going to really use low dimensionality, or in our case, it's going to be the minimum expected code length with respect to some dictionary. And that dictionary is going to be semantic and explainable by construction. And therefore, in this second case, the parsimonious representation is going to be explainable by design if this query set that I'm going to be talking about is explainable. So let me get into the details for each one of the two cases that I mentioned thus far. So again, the idea here is that we can take an input image, X, we can add a small perturbation to it, and we can produce another image that is nearly identical to the first image. And if we do that, the performance might go from 99% to nearly 0%. And why does that happen? So how are these attacks or these perturbations delta computed in order to make the system fail? This is here a deep network parameterized with parameters theta. And you, I don't know why the clicker is not working. And so the delta here is the perturbation. And so what you do is that you choose the perturbation delta to maximize the loss with which you train your network. And there are lots of sets that you could use in order to define what small means. The classical and the simplest way, and this is probably mathematical convenience, is simply to say that they lie in a small ball of a certain radius. So epsilon here denotes the radius, and p here is the p norm. Okay? And so as a consequence, most of the computation of these adversarial attacks is simply solving an optimization problem. And the optimization problem can be solved using gradient ascent, or for whatever reason they call it gradient ascent, but it's gradient ascent. And so that's the famous PGD algorithm that all it does is to try to maximize the loss with respect to delta. The critical point that I'm trying to make, which will be relevant to the talk in 2 or 3 minutes, is that you need to compute gradients of the map F in order to compute these attacks, okay? What are now ways to defend against these attacks? There's been a large number of defense methods, but one of the most commonly used today is adversarial training. Namely that during the training process, we present the algorithm not only with the original data, but also with examples that are perturbed examples, where for each training example, you compute an attack in the way that I mentioned later. There are other methods, but this talk is really more connected to the denoising style defenses, where we take the corrupted example, x prime, and we try to reconstruct the original x in order to have a x that is not attacked. And this has been going on. People propose an attack, people propose a defense to patch the attack, and you have these cat and mouse games where you get better and better attacks. But after many years of doing this, what seems to be working in practice, adversarial training continues to be used, but the challenge is that it's computationally difficult, because for every training example, you've got to generate these attacks. Now, it is true that you can defend, again, a specific attack. But the problem is also that if you make an algorithm that defends for one attack, it may not work for a different attack. And so here's one example. The rows here correspond to different attacks. These are the norms. L infinity is the attack that I mentioned in the previous slide, with the infinity norm, 2 norm, and 1 norm. The first column here is the performance. When there is no attack, you can do 99%, 98%. When you get attacks, that's what I mentioned earlier. You get 0 or 48, 44% accuracy. These different columns are, if I defend the algorithm with adversarial training, train with examples with L infinity norm attacks. This is the defenses with L2 attacks during training. And as you can see, the main thing I want to point out is that the diagonal 90.3, 69.2, and 74.6 are much larger than the off-diagonal terms. Meaning that if you do adversarial training with the correct norm, then you get better performance. But if you say, do adversarial training with L infinity norm and then test with L2 norm, then the performance is not as good. Now, it is possible, of course, to do adversarial training with all possible attack families that you might want to have, but this becomes really costly, because for every, as you're doing the training, you need to generate new attacks, right? The attacks keep changing as the network is being trained. So it is possible to, if I had a family of 100 different kinds of attacks that someone came up with, we could potentially do adversarial training with all possibilities, but that it's really computationally challenging. So the goal of this work is to try to reverse engineer the process, because if I could figure out what was the attack family ahead of time, then I could potentially have a defense that is specifically targeted to that family. And more broadly, what we're going to do in this paper in particular is the question of whether we can do both at the same time. Namely, if you give me X prime, which is the attacked image, can I recover the clean signal? And can I recover the attack? And if I do, then I can classify each one of them potentially independently. So I could solve my classification task now on the clean images, And I could also identify which attack family was the one that attacked this thing. So that's exactly what I just said. We're going to take X prime and we're going to decompose it as the sum of a clean signal plus the attack, and then classify each one of the two independently. And in order to do that, we are going to use block sparsity to represent both the clean signal as well as the attack delta. Why do we do that? Where do we draw inspiration to do this? There was this great work by John Wright and Yi Ma in 2008, where they were trying to do face classification with corrupted images. And so you begin at the left with an image of a face that's been corrupted, and you decompose that image of a face in terms of a dictionary. And the dictionary here is the clean training examples. And this dictionary has a collection of different blocks, the red, the blue, and the green block, and they correspond to faces of different individuals. And then, if you try to do a decomposition as, the X prime, I write it as a sparse linear combination of this dictionary, you typically get coefficients that are sparse, and you get non-zero coefficients. These red coefficients come from the red block because the red block corresponds to the correct identity of the person. And then there is a residual, and this residual is also assumed to be sparse, meaning that not the whole image is attacked, but only salt and pepper style noise in a few pixels. And so what we did later was to enforce block structure, because you could get a sparsity level of 3, let's say 3 non-zero coefficients, but these 3 non-zero coefficients could correspond to 1 red, 1 blue, and 1 green. And then you would not be able to identify the correct class. And so what you want is the block to be non-zero, not sparsity on the coefficients. And both works came with a lot of theory and analysis. For the first case was the cross-bouquet model with conditions in which if you do this, you could recover the exact original X and the exact perturbation delta. And for our analysis in 2012, we had conditions under which you can recover the correct block, which gives you therefore the correct class by constructing, and the correct delta. But all of this work from 15 years ago, delta was just a perturbation. There was no notion of it being adversarial or notion of it being an attack. Moreover, as you saw from the previous slide, these adversarial attacks are typically dense. So it's not necessarily the case that we can use sparsity on delta in order to solve the problem. So the key question was, well, how do we maybe take insights from this work of 15 years ago, but now adapt it to the adversarial setting? And what do we do about this delta, which is no longer sparse and no longer, fully random? It is actually a crafted attack based on the gradient to a particular network. So what we do appears to be extremely simple, and I'll explain why this makes sense in the next 3 slides. So for the time being, just follow me. What we're going to do is to simply, it seems very naive. I'm just going to take the delta, the second term, and replace it by another dictionary. So what do we do specifically? We're going to have 2 dictionaries, one dictionary DS for the signal. And this is the same thing as before. It's going to have 1 block for all of the training examples from class 1, the red block, the blue block, all of the training examples from class 2, and so on and so forth for all the classes. So this doesn't change at all. The main change is that we're going to do the same thing now for the attacks. We're going to have 1 block that corresponds to attack family number 1. Say this could be the P equals to 1 in the LP norm. The second block is going to be, say, P is equal to 2. And for each family of attacks, you're going to have a different block. But then within each block, we're going to have a sub-block, which corresponds to the fact that we can compute attack family number 1 for examples from class 1, or from examples from class 2, 3, 4, and so on. So each sub-block here, as you can see, it depends also on the class. Okay. So as a consequence, we have a 2-block structure, one that comes from the family of attacks, and a second block that comes from the class of the signal. And therefore, the dictionary of attacks is nothing but you take your training examples, you take your family of 100 different attack types, and you just compute the attacks for each one of those families and for each one of the training examples. That's what the signal is. And then with that in mind, we're going to do something super classical. We're going to try to reconstruct the attacked example X prime as a linear combination of both the signal dictionary and the attack dictionary. And we're going to minimize two group style norms. These group norms are simply trying to encourage that you want the block that is obtained from the signal block to correspond to only one class. And likewise, the attack needs to come from the correct attack family, but also from the correct class. So the CA actually has this two-block structure, as I mentioned earlier. And this 1,2 norm is nothing but the sum of the two norms within each block. So you might wonder, well, why? Why does this make sense? So the first question is, why can we assume that X prime has this block sparse decomposition? So for the signal part, this may or may not be true, and this is your classical setting, right? For phases or for many of the computer vision examples we worked out 15 years ago, if the signal does come from multiple classes and each class comes from low-dimensional subspace or has a sparse representation, then we can apply this. So the interesting aspect of the work isn't really why this works for signals, which it's already known for the last 15 years, but why does it work for the attacks? So are there networks for which we can assume that the attacks do have this block sparse? And here is one example. This is true if the network is a ReLU network. And why is it true? As you know, the input-output map of a ReLU network is piecewise affine. So this means that for a particular X, the input-output map is a affine transformation. And remember that I said earlier that these attacks are computed by computing gradients. And so as a consequence, the gradient of the output with respect to the input is at a particular X is just going to be a linear function. And so effectively what happens is that you take the input space and you divide it into different cells. And for each cell, you have a different affine map. And therefore, for each cell, the gradient, they're linear combinations of each other. Okay? Therefore, if I have a number of training examples, say in the yellow cell, and now at test time, I'm going to have a different X, but the gradient of the network at that different X is going to be a linear combination of gradients at training examples in the same cell. And therefore, that block sparse decomposition does exist to begin with, because you're always going to say for a test example, the gradient, which is all of the attacks are going to be based on those gradients, are going to be linear combinations of only gradients from that block. And therefore, you have a one block sparse decomposition when you consider all the gradients of all the cells. So that's the first contribution. The second one is theoretical, like the same question we would ask 15 years ago. If I give you a corrupted X prime, can you decompose it as the sum of a clean signal plus the attack that you used? And so the question is, what are the conditions on this dictionary? The DS is, again, the set of training examples. And the DA is, again, the set of all attacks applied to all training examples. Under what conditions under those dictionaries can I recover the correct signal class and the correct attack class? And you saw from the tutorial yesterday and from classical sparsity that when you do that for L1 minimization, typically you have null space conditions or incoherence conditions or restricted isometry properties. When you're trying to recover blocks and when you're trying to recover classes, you don't care about a unique sparse solution. You care about recovering the correct block. That's sufficient to determine the correct class. And so that is much more related to the subspace clustering literature, where you look at subspaces and you want the subspaces to be sufficiently separated in order to determine the correct class. And so extending those results to the L1-2 setting and to the adversarial setting, which is what we have here, the theoretical result is effectively of that nature. So there is a particular correct class I and a particular correct attack family J, and that defines a sub-block of the dictionary for both the signal and the attack. That sub-dictionary spans some subspace associated to, again, the correct class and the correct attack family. What this theorem says is that if you compute, this is the far right here, the theta 1, 2 is sort of the angle between that true subspace and the atoms of the dictionary corresponding to all other blocks, okay? So that angle needs to be sufficiently large. That's what it says. That's what on the far right here. And so this means that all of those blocks of the dictionary that I was talking about need to be sufficiently separated as measured by some angular distance, theta 1, 2. And that angular distance is adapted to the norm we're using. Okay. On the left, that gamma is a measure of how well distributed the atoms of the dictionary are within the corresponding subspace. So what the theoretical condition is then on the training data as well as the attacks is that you need the atoms of the dictionary to be sufficiently well distributed within their subspaces. And then between the true subspace and all other subspaces, they need to be sufficiently well separated. Okay. Last challenge is computation. How do we obtain this sparse decomposition? By and large, this is standard algorithms at this point, right? You just run your favorite block sparse. The challenge is that these dictionaries are now very large. In the work of 15 years ago, it would just be the number of training examples. Now is the number of training examples times the number of attack families. So you cannot expect to solve this efficiently, and you need to do this for every, at inference time for every example. So what we do is to exploit what we know. We know that only one block, in theory, should be non-zero. Right? So therefore, rather than using the whole dictionary, we can ideally just select one block. Now, the question is always, of course, which block should we choose? Right? So that's exactly what we do. We have an active set algorithm where we relax the problem by putting some penalties on the regularizers. You know that if the penalties, lambda s and lambda a, were very, very, very large, then the optimal solution would be with the coefficients being all zeros. So that's the sparsest possible. And you know from homotopy continuation methods that as you reduce the lambda little by little, you eventually are going to get to a solution that has one block that is non-zero. And so that's what we do exactly. From the optimality conditions of these convex problems, you can determine what is the value of lambda that allows you to have one block that is non-zero. And so the details, you can attend the poster. I think Darshan is here, and he'll be presenting the details this afternoon on how to do all of this, so you can ask him. But by and large, that's the idea, that we can solve the problem efficiently by having a method that allows us to select the right block in a greedy manner, and then we can do this more efficiently. You will see in the poster many more evaluations, but here I just wanted to summarize what happens in practice. This is on the MNIST data set, so if you have a network, you train it, you get 99.99% accuracy. If you attack the CNN, now the accuracy might be 20-something%. If you do adversarial training, you get back the accuracy to 75%. In this case, all we did was to solve a sparse decomposition of the attack signal and use the selected block to determine the class and use the selected block to determine what attack family it was. And you can get above 80% accuracy. So you can actually do better than adversarial training, and you can do better than even taking the clean signal and passing it back through the original network. So even just the sparse decomposition and these block sparse classifiers do better than the networks themselves. Of course, this is true for simple data sets for which this block sparse assumption on the signal makes sense. So this works, and you will see in the poster, for faces, for MNIST, and those kind of data sets. But the key open problem is how do we extend these to signal classes that cannot be well approximated by these block sparse decomposition on the signal space. And we are actively working on that at the moment. So in summary, for this first part, how low-dimensional representations help robustness. The key observation is simply that these attacks are based on gradients, and for ReLU networks, these gradients can always be expressed as sparse linear combinations of other attacks. And we also derive conditions on the data and the attacks under which this block sparse recovery is guaranteed to give you the correct class and the correct attack family, and develop efficient algorithms to do this in practice. Let me move now to the second topic, explainability. So as we know, this is a critical problem today, and the challenge is that when we look at the way in which explainability is done today, is done in a post hoc manner. You look at a network, the network makes some predictions, and then you try to look at what regions in the image were most relevant for that prediction. There are lots of methods to do that, but the simplest, the original ones like GradCam, they simply are sensitivity style analysis. I compute something like the derivative of that pixel prediction, whether it's class 1 or class 2 or class n, and compute the derivative with respect to the input image, and I look at which regions in the input image I have high activations. And when you look at the results, well, is it really explainable? I think people just end up debating as to why the network came up with this region. And in the case of medical applications, you can have regions that are red, therefore they have high explainability power, but they have nothing to do with what the prediction was being made. So the good way, the good thing of doing this post hoc analysis is that, I have a high performing network. I know it works very well. I don't need to retrain it in order to produce an explanation. But these explanations might be really bad, and it's not clear why they are true explanations. Many people are extremely concerned about this. Here are some quotes from Zachary Lipton, who is really worried about the state of the art in explainability of deep learning. So what we advocate is to do things backwards. We should really be thinking about explainability from the beginning, not at the end. So we need to do the following. We think that an explanation is not just a region, but for the end user, it might need to be an explanation in terms of words or patterns about the reasoning that led to the decision of the network. We think that the explanations are not unique. They depend on the task. They depend on the user. For example, if a medical doctor is explaining a diagnosis of a patient to another medical doctor, number one, it's going to use a particular vocabulary that is targeted to medical diagnosis. The way in which that clinician explained that diagnosis is going to be different if he or she is explaining that to another clinician versus whether it's explaining that to the patient. And therefore, the explanation needs to be adjusted to the user and depends on the task and depends on the domain as well, because the vocabulary is going to change depending on what is it that I'm trying to explain. One way to capture this idea of explaining things in terms of words and in a way that is task-dependent and user-dependent is by letting the user tell you what is a good explanation for he or her. And the user can do that by providing a potentially large number of questions about the predictions. And the AI system will be expected to answer each and every such question. It's like you're listening to my talk right now, right? I'm a poor speaker, you're going to understand just a fraction of it. But at the end, there is a question session. So you can ask questions. And if I realize, based on the questions that you asked me, I realize, okay, I didn't explain this very well. I'll adapt my explanation as well. Some people ask me, is the user going to provide you a large query set ahead of time? Well, it turns out that for many applications, you can come up with the query sets naturally. So here are 4 different examples. On the top left, the task is to classify birds. And I have no idea how people classify birds, but the expert typically look at attributes. So is the belly yellow? That might be a natural. And there are data sets already that comes annotated with attributes about the birds. In the middle one, the task might simply be to describe the scene with a caption or describe the content. At this point in time, object detectors are working fairly well. So the queries could be, is there an object of class 1, 2, or 3 in this region of the image? And that already gives you a very large vocabulary of such questions, because for every object class times the number of bounding boxes in an image, that's the set of all queries that you ask. You also have ways of asking for relationships between pairs of bounding boxes. On the right here, this is medical diagnosis. What's the way people are diagnosed today? Well, you go to the office and they ask you, do you have this symptom or this other? Or then each test can be considered as a query. So this sequence of questions about symptoms that the patient might have are relevant to making a prediction as to what is the diagnosis. And then at the bottom left here, this might be a classification of a document. There are lots of ways in which you could find the query set. What we did in this work is the trivial. Is a particular word present or not? So we selected on the order of 1,000 words, and the queries are really, is the word present in the document, yes or no? So once you have this query set, which is application dependent and user dependent, the deal is the query set might have 1 million queries. And here is where low dimensional representations come to the rescue. What you want to do is to select a very small number of such queries. How many of you have played 20 questions? Right? So you can, I've even done this with my 10-year-old son, right? I said to him, hey, I have a number in my head from 1 to 10. Ask me a question. He said, is it more than 5? Why did he do so? Because you split the space in half by asking a question that is the most informative question, right? And so the idea here is, can I come up with an algorithm that will sequentially select out of 1 million possible queries, the first one to roughly split the decision into half, and then condition on the first one, I select the second. And so this is the output of our algorithm, by the way. For this input image on the left, it's selected as a first query whether it has a shape perching like. And the answers here are yes, no, yes, no. And then the algorithm stopped after 7 questions here out of 300 attributes. And it predicted with 99% probability that this is a green jay. And we're going to see various examples throughout the talk as to how the probabilities of what class it is changing after 1 question, 2 questions, 3 questions, and so on and so forth. What is an explanation now? I predicted with 99% probability this is a green jay. Well, here's the explanation. It is a green jay because it has a shape Pershing-like, and it does not have upper part colors that are yellow. Okay. So the sequence of questions and answers that the algorithm produces immediately provides the explanation for why that prediction was made. Okay, so that's the motivation. So how do we actually do it? So first, we need to define the queries. I already touched upon that, and for now, for this talk, I'll assume that the queries are given, and I gave you 4 examples of what those queries are. The next is, how do we select the queries? So as I already said, and this is the correction here, we're going to select the smallest possible number of queries that are sufficient for prediction. So minimality and sufficiency of this is the definition of a parsimonious representation here. The algorithm is going to be information pursuit, which is this algorithm that selects 1 query at a time based on information gain. And this is going to have connections with information theory. Naturally, each query can be interpreted as a bit. This sequence of queries is sort of a semantic code for the scene. And the principle based on which we stop is the concept of semantic entropy. So, mathematically, what do I mean by that? So, capital Q is going to denote the set of all possible questions that I can ask. And when capital Q is applied to a particular x, that's going to denote the answer to that question. So Q is the question, and Q of x is the answer to the question for x. And when I use capital letters, is because I'm talking about all possible questions and about any random input x that I could potentially consider. So what do I mean by sufficiency? We're going to ask a sequence of questions up until I'm satisfied. Okay, how do I write that down mathematically? What we want to do is to predict y given x. So we want to estimate the posterior. That is the definition of the task. The idea of a query set being sufficient is simply that rather than that the prediction of y given x is the same as the prediction of y given the answers to all of the queries about x. So again, this is the idea when I'm trying to classify a bird, that I don't need the image of the bird. I just need a small number of attributes for the bird, and those are sufficient for predicting y. And this is just captured mathematically by saying that P of y x is the same as P of y given the set of all answers to queries about x. And so with these definitions, each query is a basic unit of semantic information, so it acts as a bit. And the set of all query answer pairs define my code. The code here depends on this letter E, because I have to have some algorithm that I have not told you yet that is going to select what queries. Okay? And depends on Q, because obviously the query set is given. So here is the notion of the algorithm that I was going to talk about. We're going to have some encoder that, given the input, it's going to select, in this case, 5 queries out of 1 million possibilities. That's the encoder. And then the decoder, what needs to do is, given the sequence or the history of questions and answers, is going to predict the posterior. It's going to predict the class of y, just given the attributes, let's say, given a small number of attributes. And so here is the definition of semantic entropy. So what we do is the following. Here on the right, you've got the code. This is the sequence of questions and answers about x that this algorithm E has produced. This bar is just the cardinality. So this is nothing but the number of questions and answers that you've asked. And then you compute the expectation with respect to the input x, which is a random variable. So this is the expected number of questions you need to ask in order to predict, say, the class of the bird with high probability. And what we want to do is to select the encoder, which is the algorithm that selects the question, so that you minimize the expected code length. Subject to the constraint of sufficiency, which is that the code that you produce should be sufficient for predicting y. And that's the constraint that P of y given x is equal to P of y given the code. Now, how do I parameterize the encoder? How do I solve this optimization problem? Well, before I do that, actually, there are a few theoretical properties of this method. First, what is this notion of semantic entropy between x and y? In some particular cases, it reduces to classical notions you're aware of. So if what you're trying to predict, y, is the same as x, namely you have a reconstruction task, and you're allowed to ask any possible binary question about x, then semantic entropy reduces to classical Shannon entropy. The second property is sort of related to classical coding theory that said that the entropy is within 1 bit of, the expected coding length is within 1 bit of entropy. The same thing is true if y is a function of x and q is the set of all possible binary queries. Then this notion of semantic entropy is going to be bounded below by the entropy of y and bounded above by the entropy of y plus 1. And there are other properties that I think are going to be useful for multitask learning problems where, well, the first two are sort of the obvious ones, that the semantic entropy is non-negative, that if the x and y are independent, then the semantic entropy is 0. But the last one is probably useful for 2 tasks. What if I compute the semantic entropy for the same x? I have 2 tasks, y1 and y2. then the semantic entropy of the joint task is bounded above by the sum of the semantic entropies of the individual tasks. Okay, going back to computation. The challenge is that computation is generally intractable. And so you need to have an efficient method to do it. We will exploit the fact that out of the million possible queries that I'm after, I probably just need a small fraction. And so we do this with a greedy algorithm that was proposed by Don Gieman in 1996 called information pursuit. So here's how it goes. The first query is selected as the query little q that has maximum mutual information with respect to y, which is what we're trying to predict. Notice capital X and capital Y here are random variables. So this first query is selected without looking at the input image. So this is like what the example that I gave you about my son. I just tell him, ask me a question, and he said, is the number more than 5? Well, he did that without looking at the number. He doesn't know what number I'm looking at, right? And so the first question, therefore, is going to be the same no matter what the input image is. It's the most informative one. The second question is the one that it's dependent on the image. So little x here is the input image. So now you're going to do the same, select the query that is most informative with respect to y, given that I know the answer to the first question. In fact, this is very related also to PCA. PCA is a particular case of this, where you select the first principal component, then you select the second principal component, but it needs to be independent from the first, and so on and so forth. But the criterion of maximizing mutual information is always the same. And so on and so forth. And then eventually you stop, and you stop when all remaining queries are uninformative for y, given the queries you have thus far. So how do you implement this? Well, at each step, you need to compute that damn mutual information. And do we know how to do that? Well, we have formulas. But when x is 1,000,000 pixels and y is many classes, you actually need a generative model to compute this. So before I even do all of this, I need to have a model for the joint distribution of images and the answers to queries and y, which is what I'm trying to predict. There's been 50 years of research in computer vision as to building generative model for images. It was nearly impossible to get them to work. When GANs appeared a few years ago, it was the first time there were some generative models that were good. But you've seen it, right? The last 5 years have been amazing progress on getting good generative models for images. Here, the thing is a little bit more complex, though, because we need not only generative models for images, but we also need, we need to compute conditional mutual information here. It's conditioned on the answers. So it's like, can I have a generative model for MNIST digits conditioned on the fact that pixel 2,3 is black? Once I have a second query, it's conditioned on these 5 pixels, I know them. This is nearly impossible because you're going to run of training examples very quickly because you might have begun with 80,000 training examples for MNIST, but after you put a few conditions, the number of training examples is going to be dramatically reduced. So this is a big challenge of training generative models that can solve this problem. So we've tried 2 things. This is exactly what I just said. Need a joint distribution of Q of X and Y given the history. And this is extremely hard to estimate empirically. The first thing we tried was simply to use variational autoencoders, which allow you to do conditioning. Explaining this slide it should be several slides. So I'm not going to get into the details. So think for the time being that is one of your favorite generative models. But still, training these models requires sampling. It requires, and this is very, very costly to do. I don't have the precise numbers, but let's say classifying MNIST digits with this approach ended up taking, I don't know, several minutes to just do one image as opposed to milliseconds, which is when you pass it through a neural network. Right? So recently, and this is unpublished work, we came up with a variational formulation that allows us to speed up this significantly. So rather than taking images, queries, and answers and building a generative model of everything to then just compute mutual information, and then we not only need to compute mutual information, we just need to actually maximize it. We need to select one query that is maximum. Well, that's just a means to an end. We don't need to do that. If I had a mechanism that tells me what's the most informative query, I don't care about the precise value of mutual information. I just need to know which query is the most informative. So this is exactly what we do now. We're going to have two networks, one, which we call the querier, that selects the next most informative question. The other one is the standard classifier that selects what the class is for that input. And so this is now based on this history of questions and answers. So at the very beginning, this is empty. I know nothing about the input image. So the classifier will probably predict 1/10 for each MNIST digit. It will give you the prior. And the querier is now going to try to select what query to ask about that MNIST digit in order to predict its class the best. And it does that according to this mutual information criteria. But as it turns out, we were able to prove analytically that finding the query that maximizes the mutual information is the same thing as minimizing the KL divergence between the posterior and the posterior conditioned on the history thus far and the new query that I'm asking. And therefore, we can use this right-hand side, the KL divergence, as the criteria for training both the classifier and the querier. Okay? And then, once we select a new query, we pass it back as an input again, and we repeat the process. So this is a recursive method. Okay, let me show you the algorithm running. So what we're going to do here is apply to the MNIST data set, but in a very unconventional manner. How? You can train a network to do 99.9999. So this is a stupid example. But rather than doing it as usual, we want to do it in a way that we select only one pixel at a time, or maybe one patch at a time. So at the very beginning is, can you predict what image, what class this is without looking at the image yet? But then tell me, what is the most informative patch? So here is the algorithm running. At the very beginning, this is an image of a number 2. So this is the input. What you see here is what the algorithm sees. At the beginning, the algorithm sees nothing. And what you see here is what the algorithm predicts. Is 1/10 for each one of the classes. Which 3x3 patch should you look at first? Okay, you can guess that it's probably going to be in the middle, right? Looking at a pixel in the corner, they're all black. So that's uninformative. So that's the pixel, and this patch is the same for every input image of the MNIST data set, because it's the most informative one according to the generative model, if you wish. Given that, and you can see immediately that the distribution changes, right? The algorithm now thinks that it's possibly a 0, possibly a 2, possibly a 6, possibly an 8. All of those numbers are consistent with that patch being white. Given that that patch is white, the algorithm next selects this one, and now it thinks that it's more likely to be a 2. This is the third most informative, fourth, and you can see how the posterior is changing. Here, the algorithm is a bit confused. It thinks that it could be a 1. This is after seeing just 5 patches. And look, a 1 is probably consistent with those 2 patches being white and the other 3 being black. But it takes, here, it thinks that it could be a 0 because it saw that white patch on the right. And the 0 is consistent. A slightly slanted 0 would be consistent with that. So it took the algorithm about 8 queries to finally converge to the fact that it's a 2. And in this particular case, with 11 queries, looking at 11 patches of the MNIST data set, you were able to classify it. You can now do this for each and every image on the MNIST data set, and the average number of patches you need to look at is about 11, and the accuracy you get is 99.5 by just looking at those 11 patches. If you now look at different data sets, what is it that you can see? The KMNIST, you need more patches in order to classify it. So this semantic entropy, expected number of patches that I need to look at in order to classify binary images, it's sort of a measure of the task complexity, because the more complex the task is, the more number of patches I need to look at in order to produce an accurate classification. I already mentioned this example, so I'm going to go quickly. This is the bird example. What is being shown here is exactly the same thing as before. Left is the input image. In the middle is the prediction of the probabilities as to which class this bird is. Green means that the answer was yes. Red means that the answer was no. And with 9 queries, the algorithm is able to figure out that this is a great crested flycatcher. This is now text classification. Here, the main thing I want to tell you is that the quality of the query set matters. And we chose a very poor query set here, which is a word present or not. The key difference is that we don't do this now with 10 questions or 11 questions. Here, we needed 125 questions to determine the document. And the reason being that if the query set is whether a word is present or not, in most cases, the answer is no. You see, I skipped a lot of it, but see, you see a lot of red. Okay. And so selecting a good query is important to do it. And the last example here, this is a medical diagnosis data set called SIMCAT 200, where a patient has a sequence, there is a sequence of symptoms and whether they're present or not associated with every patient. And again, in all cases, what we're trying to do is to select the most informative symptom, the second most informative, and so on and so forth, and then predict the disease label. All right, so I think I started 10 minutes late, so I'm hopefully still in time. The summary of it is, we really think that interpretability needs to be done by design and by construction as opposed to post hoc. And we think that this information theoretic approach of selecting a sequence of queries that produce an explanation is an important step into having a framework for interpretability by design. Of course, there is lots of things to be done. Selecting the queries, what queries are adequate for each domain, how do you determine whether a query set is sufficient for a task or not? Those are all important questions. But for both applications, I think the underlying theme was that low dimensionality and parsimony are important. In the case of robustness, parsimony was in terms of block sparsity. In the case of explainability, parsimony was selecting the minimum number of queries that are sufficient for the task. Thank you very much.
For the first part, I was wondering, how do you, because there are infinitely many possible attack families, and so how do you choose the attack families and build a dictionary in a given application? And that was one question. And then the second thing was, it wasn't still clear why the linear combination of attacks inside a block would make sense. How many training signals would you need for it to be representative of an attack inside a class? So,
yeah. Great questions. So as I said, new attacks are coming all the time. And so I think this is an immediate limitation of what we've done. We need to know a priori what are the attack families, and we need to compute attacks on the training examples a priori. And that defines the whole dictionary. So the question of how you extend it to a new attack family you didn't know about, it's, I think, outside the research. We wouldn't be able to do that with the framework we've provided thus far. Computationally, it's not that much of a problem, we hope, because, as I said, the algorithm is just selecting ideally one block. And so even though the dictionary, in principle, could be very large, what you get to use when you're computing is very small. The second part of your question was, how do we ensure that you have sufficiently many representatives within each cell? So you're totally right that the number of possible cells can be combinatorially large, and you might not have enough training examples. In the way we've implemented thus far, we assumed the dictionary was attacks applied to the training examples. But the reality is that you don't need to do that. The key critical ingredient is computing a affine map that defines every cell. If you have that affine map, And that affine map doesn't depend on the input, and doesn't depend on any training example. If you were able to compute one affine map for each training cell, you could use that as a dictionary instead. And therefore, that dictionary would be sufficient because any element, even if you have no training example on that cell, if you have the affine map for that cell, it's enough.
Oh, thank you very much for the talk. So with the explainability, it seemed that the choice of the queries is really critical. Like, so for example, you know, with the birds, like it sounded like it really requires expert knowledge, for example, to know, oh, you know, like the belly is important, color of the belly and so on. And do you have any ideas on how to get like good queries, like in a principled way, maybe based on data?
Yes, so that's, I think, critical. I had that as the key open question moving forward next, but a couple of thoughts. One of them is, how do I think the way to look at this theoretically is, how do you check for sufficiency, right? Because at the end of the day, I did have that written down. And I conjecture that one approach to doing this is based on building a dictionary of queries in sort of a lifelong learning fashion. As new data is coming in, you can ask the question, is it well represented by the query set that I have thus far? And if not, can I add it? There are a lot of approaches based on clustering that are currently being explored for related purposes, where effectively at the very beginning you know nothing, and so you might just have one cluster center, and as iterations proceed, you keep adding new clusters that capture new concepts. In a certain way, some people argue that concepts are sort of made up by humans for the purpose of compression. Like, if we're going to use this concept repeatedly, we better give it a name. And then we can use the name instead of the concept. So how can we capture that and build algorithms that will be able to build a query set and eventually figure out, okay, I need a concept for this. And so I think that the idea of using some form of clustering where each cluster corresponds to a concept and you keep adding more concepts as you go along is probably the way to go. But right now, as I said, we don't have an algorithm that does so, and so those are the lines we're thinking about.
Thank you.
Yes.
Okay, thank you. This is Bihan from NTU Singapore. Thanks, Prof. René, for the nice presentation. And I'm really interested of the first talk, robustness of the adversarial denoising, because I work on block sparsity and also adversarial attack. So I think that's interesting. So good to know that this block sparse coding idea works for classification, right? But I fully understand that we have to know the type of attacks beforehand to train the dictionary. But I'm just curious, even for the same attack, if the attack, say, the budget changes, right? I mean, the L2 norm or like L1 norm, like constraint changes, will that affect the classification accuracy? Like without having additional type of attack, the same type of attack, but changing the type of, say, budget or constraint, will that affect the classification accuracy?
Yes.
I'm just curious, yeah.
I don't think we've had concrete experiments to answer your question experimentally, but my sense is the following. Unlike classical sparsity, where maybe I'm given the level of sparsity or I choose it based on a regularization parameter, when it comes to classification, you have the additional information that you know or you expect that the signal to be classified comes from one class. And so as a consequence, you're not looking for block sparsity in general, but really one block sparsity. And therefore, you can always tune the regularization parameter to just select one non-zero block. Experimentally, we have observed that if you just stop at the first block, that works worse than maybe letting it choose 2 or 3 blocks, and eventually you're going to select the top one. So it is true that in practice it's a little bit more complex than what I just said. But I think that makes what we do much easier from the perspective that we just need to select the the one block.
Thank you.
Hi. In the interpretability aspect, like you have a set of queries, right? And how is the query answered? Like it is answered by another model? If yes, then the model answering the query might not be based on like interpretable assumption, right?
Yes. Where are you, by the way? I don't see you. Okay, great.
So
Yes,
the
great
answer
question.
might not be produced by interpretable model. Like it might
Great.
be another black box model, right?
Yeah, fantastic question. So some query sets might be what are the pixel intensities in this patch. That can be automatically answered. And the example of the MNIST that I give, that's what it is. And that corresponds to sort of the classical post hoc interpretability. In the case of the bird example, you can train a deep network to predict the attributes of the bird. Some people might ask, well, doesn't that go against the principle? It's like, that is not explainable anymore. I think it's critical in interpretability to choose the right level of resolution at which you want the explanation. And for the bird classification example, the right level of semantic resolution was what are the attributes of the bird. More generally, depending on the task, you might need to do some pieces of it in an uninterpretable manner, and you just need the explanations to be at the right level of semantic resolution, is what I would argue. And so it is perfectly fine to train and leverage state-of-the-art systems in order to make the predictions and the answers to the queries. I gave the example of using object detectors as one other example if your queries are whether an object is present or not in a different region of the image. So long story short, how do we answer the queries? You just train. For example, you could use a visual question answering system if you wanted. Or depending on what the query set is, you just train a network to answer them. What we have not done, and that's also a great question, is if you do that, then the answers to the questions might be noisy. So you need to do 20 questions with noise. There is research on that as well, and we're working on that as well.
Yeah, thank you.